Has this ever happened to you? Hey bro, do you like music? I prefer painting, but I enjoy a good song every now and then. Okay man, you have to check this out. What's this? Well, it's Chopin's Nocturne in B flat minor, of course. And why are you showing it to me? Because it's the most beautiful piece I know. And now, picture this. Hey bro, do you like math? I prefer music, but I enjoy a good math problem every now and then. Okay man, you have to check this out. What's this? Well, it's Pythagoras' theorem, of course. And why are you showing it to me? It's the most beautiful mathematical concept I know. Both scenarios are quite mundane, and it would be really hard to appreciate music if you couldn't actually hear it. And the same could be said about math. However, we can't really hear math, but we can understand it. If music's medium of expression is sound, math's media are ideas and concepts. Are you actually comparing math to art? Yes, I am. And it all started with this book. The Book of Elements. It is one of the most influential works ever written. In fact, since the invention of the press, it has been outprinted only by the Bible. Some consider it to be the precursor of pure mathematics, or even the birth of the scientific method altogether. This work is attributed to Euclid, a Greek mathematician who lived around 300 BC. But why is it so important? This book is made up of 13 volumes of definitions, axioms, propositions, and mathematical proofs, ranging from really basic, seemingly obvious concepts to complex mathematical ideas. The rigor behind everything that is stated in these volumes is pristine, to say the least. Every concept is described with such elegance that anyone would have a really hard time disproving anything.
Anyways, let's dive right in. This book starts off by defining the building blocks that it uses throughout the whole thing. Here, for example, is a definition of a point. A point is which has a position, but not dimension. Very concise, kind of obvious, but with this definition, it is impossible to mistake a point for something else. A line is which has length, but not breadth. Whether it's a finite line or an infinite one, as long as it has length and no width, it is a line. Planes, figures, angles, triangles, types of triangles, and circles. Note that any point on the circumference of a circle is of equal distance to the center, which is also kind of obvious considering that defines a circle. You could compare these definitions to notes in music. Notes are defined by specific frequencies, and the way you arrange the different notes together will give different results.
Then there are axioms, which are things that are regarded as self-evidently true. For instance, the whole is greater than its part. That's just logic, right?
And we get to our first problem. Using a straight edge, which is basically a ruler but with no markings of measurements on it, and a compass to draw circles, you can accomplish and prove various things. Ideally, this could be done in your imagination. You are given a line of any size. Call it AB. How can you make an equilateral triangle with it? Well, first, draw circles on the points of either end of the line with radius AB. Next, where the circles intersect, call that point C. Choose one of them and connect both points A and B to it. Since both circles have a radius of AB, and because of the definition of a circle, that at any point on the circle its radius remains the same, AC and BC are the same length as AB. This forms an equilateral triangle.
This sounds like a really basic idea, yet there's really no way to disprove it. Here's the thing with the Book of Elements. Before it, mathematics were done for more practical uses. The Pythagorean theorem had an older proof that used a triangle with sides of length 3, 4, and 5. Put that into a squared plus b squared equals c squared, and it works. But that doesn't say much about all right-angled triangles. In fact, most mathematicians would be dissatisfied with a proof such as that one. Euclid's proof for Pythagoras uses geometry, congruent triangles, and similar angles. With Euclid's elements, we are not solving a problem. We are solving a condition for all time.
In this second proposition, you are given a finite straight line, BC, and a point, A. You must create another line from point A of equal length to BC. First, we'll join point A and B. With this new line AB, form an equilateral triangle. We know how to do this now because of the first proposition. Call this triangle ABD. Create a circle with point B as the center, and this line BC as the radius. Let line BD join the circle. Call the meeting point E. Next, form a circle with point D as the center with the radius DE. Finally, let AD join this circle. Let the meeting point be called F. Lines BC and AF are of the same length. We know this because lines BE and BC are the radii of the same circle and therefore are the same length. Then, we know that lines DE and DF are also of the same length because they are also the radii of the bigger circle. Finally, because the triangle ABD consists of sides of the same length, we can conclude that the line AF is equal to the line BE, and therefore also the line BC.
Throughout history, some people considered that you were not a real academic unless you'd read and thoroughly understood the Book of Elements. Over those years, many brilliant minds have added and modified the Book of Elements to a point where it's hard to tell exactly what the original was. Today, you may want to read the Book of Elements in order to enjoy the art of geometry and logical reasoning. And although the concepts themselves may not have any real-world applications, they are works of art in terms of how you can arrange ideas and come up with universal truths. Similar to how a composer would write the most perfect piece of music. There is nothing really useful about either of those things. However, I'm sure that very few people would enjoy music if this was the only way it has ever been presented to them.